This video is a workthrough of the first question provided in the practice problems for Newton's laws, and I wanted to show you this full solution in detail because there are some key steps that differ a little bit from when we were doing kinematics. So let's look at this question together. It starts by saying a 24.3 kilogram curling stone is released with initial velocity of 2.84 meters per second. If the coefficient of friction between the stone and the ice is 0.014, how far will the stone travel before stopping? Now, for starters, this kind of question, something like how far will it travel before stopping, that was a typical kinematics question. We used to ask questions like that in the very first unit. How far will things go? How high will they go? How long will they take? So that's a good indication right there that we're going to need some kinematics to solve this question. But we have some additional information that pertains to this scenario, and we also are lacking other kinematics information. So let's outline sort of what's been given and clearly what hasn't been given. So I know a few things. Number one, I know the mass of the curling stone is 24.3 kilograms. Notice that that's 3 significant digits. We're going to need to come back to that. It has an initial velocity of 2.84 meters per second. Let's go ahead and write out the other things that we used to do during kinematics. Final velocity, acceleration, time, displacement. And we can actually fill in some things. We know that final velocity, we know how far will it go before stopping is what's given in the question. So final velocity must be 0. Acceleration, we don't know the rate that it's slowing down, so that's a question mark. We don't know how long it was traveling for, so we don't know that either. And this displacement, actually, it asks us that. That's what it's asking us to find out. How far will this stone travel before stopping? So this is what we need. Okay. But there is one other bit of information, which is this piece right here, coefficient of friction. And we know coefficient of friction is this mu, okay, and that's given to be 0.014. Okay, so it's pretty clear that friction is going to play a role in this question, so we don't want to ignore that value there. So step one, identify variables. We should also have a clear picture of what's happening here, so let's try and draw that out. Here's our ice, and on the ice is a curling stone. Okay, we know that it's traveling in this direction, and that it will eventually slow down and come to a stop at the end. So this is where the curling stone is going to be. Now, what are the forces that are acting on this object? Because unless we can identify clearly what all the forces are, we won't be able to start to analyze the physics. So we know that obviously we have a force of gravity. Force of gravity pulls down on all objects. Okay, and when it's being pulled down, then the ice surface pushes back up again. So we also have a normal force. Force normal. Those are equal in magnitude but opposite in direction because the amount that gravity is pulling it into the ice is the amount that the ice is pushing it back. We know that because it's neither falling through the ice or flying off the ice. Now, what other forces are happening here? Well, we know that somebody may have initially pushed it. Okay, so there may have been an initial horizontal motion, or at least a horizontal force to the right-hand side. But I want to emphasize here that in the question it says that the curling stone is released. Okay, so if the curling stone has already been released, then there's nobody pushing it, and therefore there's no reason to put a forward-facing horizontal force. It's simply not being pushed. However, it is slowing down, so we know that there is a force of friction acting on the object that is trying to slow it down and pull it backwards. Okay, so those are all of the forces put together, and I can actually know right now, given that Fn equals Fg, that I don't even need to really worry about those two forces, those two values, because they cancel each other out. So really the only force that's really of particular importance is this force, the net force of friction. So we can actually write here that we know that the net force is going to be just equal to the force of friction. That's the only force that is going to have any effect on the overall motion. So let's actually get to solving this, because we've laid out a good free body diagram for forces, and we know what all the variables are, what's given and what isn't given. So from a problem solving standpoint, essentially we know that we want to solve for displacement, and there are things we know and things we don't know. If we were just dealing with kinematics, then this would be an impossible question. We would have these values. Remember, kinematics, VI, VF, AT, and D. We need to find D, but we don't know TA or A. Okay, we only know VI and VF, and we can't solve. There's no equation that would allow us to solve for displacement because they depend either on acceleration or time. Okay, so if it was just kinematics, we would be stuck. But this isn't just kinematics. We actually know something about the forces, and the critical piece here, and I'm going to have to emphasize this over and over again, is that this acceleration is the link between kinematics and dynamics. Okay, because remember, kinematics, we had acceleration showed up in a lot of formulas, and in dynamics it shows up in one really important formula. Okay, it's Newton's second law. It tells us that F net equals mass times acceleration. Okay, so we could in fact use Newton's second law to find acceleration. All right, we know something about the mass, and we probably know something about the net force, since we just talked about it up here with force of friction. So if we know that net force is equal to friction, and we can put it in there, we also know what the mass is, then we could solve acceleration. And from that point on, we're pretty much well on our way, because acceleration will be substituted in here, and now we have VI, VF, A, and we can solve for D. Okay, so let's actually do that math and see how it plays out. So we ultimately want to solve for acceleration, and we're going to do that with Newton's second law. F net equals mass times acceleration. We know from our free body diagram that the net force on the object is only caused by the force of friction acting backwards. So F net equals force of friction, mass times acceleration. And we know that the friction is actually, we have a formula for calculating how much friction is acting on this object. It's dependent on two things. Number one, the coefficient of friction, in this case kinetic friction because it's sliding, and the normal force, which is to say how much is the surface pushing up into the object, because that's going to increase the amount of friction. So if mu Fn now must be equal to ma, okay, and we know the coefficient of friction. This was given in the question, okay? And the normal force, although it wasn't technically given in the question, well, we know that this normal force, the normal force comes around as a result of the force of gravity. The more that gravity pulls down, the more that the surface will push up again. So this normal force can be calculated if, in fact, we know what the force of gravity is, which can be calculated using mass times 9.8. So let's just do that off to the side here for a second. The mass was 24.3 kilograms, and the acceleration 9.81 meters per second, or sorry, newtons per kilogram. We should be using those units. So 24.3, 9.81. Okay, we have 238.383. 238.383. Okay, and that's going to be in newtons. Okay. So force of gravity is equal to normal force. So let's go and substitute in all the other values that we know. The coefficient of friction was 0.014 multiplied by the normal force, which we just figured out was equal to the force of gravity. That's going to be 238.383. Notice I'm keeping a lot of extra digits around in numbers. These are process calculations. I'm going to round at the very end, but I'd like to keep extra digits throughout the question so it doesn't affect the overall value, and we'll round off at the final value. And that's got to be equal to the mass, which we know was 24.3 kilograms multiplied by acceleration. Now, in actual fact, we should be mindful of the fact that friction is actually negative. So this is actually a negative value, and we're going to want to make sure that when we insert, when we come to our final answer, we're going to use the right direction when we summarize it. So let's just solve here for acceleration. So calculate the number, we get 0.13734 newtons per kilogram, and that's going to put in the backwards direction because we know that it has to be negative. It's what's slowing the object down. So now that we have this acceleration value, we can just go back to solving this question like it was a regular kinematics question. Remember, we knew something about initial velocity, we knew something about final velocity, we know we need displacement, and we just had to find the acceleration, so we've done that. So let's go ahead and now solve this question as a kinematics question. Okay, so we have all of our values rewritten here. We know something about initial velocity, we know something about final velocity, we now know about acceleration, which I've input as a negative number. We don't know anything about time, and we want to solve for displacement. So really at this point we are simply looking for a formula that solves for d that doesn't involve t in it. And that's simple enough. We know that we can look at this one. Vf squared equals Vi squared plus 2a delta d. And we're going to substitute in our values and rearrange. So 0 squared equals initial velocity, which was 2.84 squared plus 2 times negative 0.13734 multiplied by displacement. And if we rearrange, we get that displacement is equal to 0 squared subtract 2.84 squared, all divided by 2 times negative 0.13734. Run it on the calculator, and we would get 29.363 meters. So that's really what the question asked us to solve. It said how far will the curling stone travel, and we just were able to solve that it would be 29.363 meters. So let's write out a final statement where we actually round to significant digits. Therefore, the stone will travel. And I think if we go back to the question, the number of significant digits for all of the different variables that were given, including the coefficient of friction, the initial velocity, and the mass, all had 3 significant digits, so we have to make sure that we're only rounding to 3 significant digits. It means we want to keep this one, and we'll let this value determine if it should be rounded up or down. So our final answer would be 29.4 meters, and we should probably put east or forward or some sort of direction. Let's just say forward. So there we have it. That's our final answer to the question. There are lots of steps involved here, and it's a great way of tying together the kinematics things from the first unit to the dynamics things. And if I can emphasize one last time, the critical piece is that acceleration. You will need Newton's second law to connect forces and free body diagrams to kinematics and solving for different variables like speed or displacement. So don't forget, you're going to need Newton's second law in there. Solving for the acceleration is the connection between those two places. Best of luck.